Okay, so to finish this case, a ray going in parallel to the principal axis is going to get reflected in such a way that it's going to appear to pass through F on the opposite side of the mirror, and then a ray that appears to go in such that it passes through C is going to reflect back out along C. Where the purple reflected rays cross will be the head. Where the green reflected rays cross will be the feet. Here is my image. Take a look at the little guy. He's right side up. So image is virtual, erect. So looking a lot like the one up above, which was the last case in the concave mirror, except that it is smaller and it is behind the mirror. Okay? So there then are our 6 cases. If I could zoom out, here were the last 3. Okay, there's only one case for the diverging mirror, and there's only one case because it doesn't matter where you put it here, the image is always going to be behind the mirror. Okay, so only one case for the diverging mirror. There isn't, like, we can't put it between F and C like we could for the other one. It's just always going to be in front of the mirror. All right, the other good news is the same equation works for diverging mirrors. So our 1 over F is equal to 1 over dO plus 1 over dI equation works. It's just that now you need to remember, if they give you the F for the convex mirror, for a diverging mirror, it always goes in as negative because we say it has a virtual focus. Okay, simply because it's on the virtual side of the mirror. So this evening I would like you to do, or for homework following this video, I would like you to do the questions on page 377, numbers 9 to 12, and these are with the convex mirrors. And then on page 388, numbers 4 to 9, and these are with mirrors in general. Maybe there is one other little piece, since we have a little bit of time left on this video, one other piece that I could talk to you about. Looking for a sheet of paper that has a blank spot. How about this one? Sometimes there's a problem with mirrors, curved mirrors, and that problem is called spherical aberration. Okay, and I'm going back to a concave mirror to show it. Okay, so here's my concave mirror, here's my F, here's my C. What we said for concave mirrors was that, rays coming in parallel to the principal axis will get reflected through F. Okay, in parallel to the principal axis will get reflected through F. But the problem, spherical aberration, arises when there are rays sent in that hit the outer edges of the mirror. Because if they hit the outer edges of the mirror, lots of times the mirror out here isn't curved enough to get these rays exactly through F. They fall a little off of F. And the result then is a blurry image. Okay? So they can't get bent enough to actually pass through F, and then the result is you get a blurry image. Okay? I'm just looking to see if they fall further. Instead, they fall closer. I drew them further out, so they're actually going to fall closer. As I was drawing it, I was thinking that. Okay, so they're going to hit and they're going to fall closer. So in the end, they don't all cross at the same spot, and so you get a blurry image. There's 2 ways you can fix this. One way to fix it is don't use the outside of the things, outside of the mirrors. Only use the center part, and you'll be okay. So that's one way to fix it. The other way to fix it is to use a parabolic mirror instead of a spherical one, right? And so the parabolic one means it wouldn't have the same radius of curvature all the way along, all the way around. It would be more shaped like a parabola, and that will cause these ones to bend better. The problem is parabolic mirrors are really expensive, and so it's better, easier to use just the center part, especially for those of us in high school physics where we wouldn't be able to afford a parabolic mirror. Okay, so it's called spherical aberration, and what happens is the rays that are hitting the outer edges of the mirror don't actually get reflected in such a way that they cross through F. They cross a little bit closer to the mirror than F, and you get a blurry image because of that. And so the easy fix is only send in rays that strike the mirror close to the principal axis. Use only the center part of the mirror. The other fix is use parabolic mirrors. The problem with that is they are really expensive. Okay? So that's the end of mirrors. When we start again, we will start images formed by refraction, which will be with lenses. All right? Oh, wait, there is one more thing. And that is, I should go back to the cases. When do we use these? It's harder to see some of these. But curved mirrors we often use, besides in amusement parks or in fun houses or whatever. We might use in other places in our lives. The one that you would probably be most used to would be this one, the diverging one. If you've ever been in a corner store that has a mirror up in the top corner by the ceiling, and you can see the whole store from it, that is this guy. Sorry, I have a tickle. That's the diverging one. We also might use them in our side mirrors in our car, where we get a smaller image and we see everything in behind. Those are the most two common uses. Okay? See you in the next video.